So the notes we're going to take today are on a phenomenon known as the Doppler effect, which we touched base a little bit yesterday. And we're going to more specifically look at the Doppler effect equation. So how can we calculate the change in pitch of an object or a sound source if the sound source is moving, or if the observer is moving, or coincidentally if both things are moving. To start, you should have out in front of you our notes from yesterday. So these notes here, if you were absent, you can get a copy of these first section of the notes from the absent bin. And I would suggest watching the video going over these notes as well. But we're going to take these notes and flip them towards the back here to our equation section. Now, we left off yesterday talking about the Doppler effect conceptually. And so the Doppler effect is a phenomenon that happens in sound where, because something is moving, whether it be a sound source, something giving off a sound, or an observer, somebody that hears a sound, but because something is moving, the sound that the person hears is perceived to be at a higher or lower frequency, a higher or lower pitch than what it actually is because of motion. If an observer has a sound source moving towards it, that sound is going to sound higher frequency than what it actually is because of the motion of the sound source. It's going to compress those wavelengths into a smaller area of space. That's going to decrease the wavelength and increase the frequency. An observer where a sound source is moving away, so instead of towards, the sound source is leaving them. Because of the sound source's motion, that's going to elongate, kind of stretch out our waves. And a longer wavelength means we have a lower frequency, or thus a lower pitch. And this is different from when we have something that is stationary, something emitting sound that's not moving, because if the sound source is not moving, then those sound waves are emitted, they're rhythmic, so they're emitted evenly throughout all directions of space. So it doesn't matter your position around the car, you're going to hear the same frequency of sound or the same pitch of sound. So our equation today, everybody should have a calculator out. So if we don't, let's take a second to pause the video, because this particular equation is going to be one of the more difficult ones we've worked with for the entire year, due to the amount of detail and kind of thinking we have to do before we pick a final answer. So we'll pause the video, get out our calculators, that way everyone can do a couple of practice problems together in class. Okay, so these notes, again, this second half here, this equation is called the Doppler effect. The Doppler effect equation. Oh, geez. Too early in the morning. Okay. So we're going to start off by writing out the equation so you can see all the variables involved, and then we'll take a second to go through each one, so what each one stands for. So we'll start off with F subscript D. As always, if there's a subscript, you got to include the subscript. So F subscript D is equal to F subscript S, then a parenthesis, V plus V subscript D, close parenthesis, over parenthesis V, and then down here we're going to put a minus, and then V subscript S, close parenthesis. Another walkthrough. Make sure all our subscripts and stuff are right. So F subscript D is equal to F subscript S, parenthesis, V plus V subscript D over V minus V subscript D. It's very important that this is a plus on top and a minus on the bottom. Sometimes we make these the same sign, both pluses or both minuses. Top has to be a plus, bottom has to be a minus. All right, so we got a lot going on here. So let's break down what is by variable. So F subscript D is the Doppler frequency. And just like any other form of frequency, that's going to be measured in per hertz. So the Doppler frequency, that's the perceived frequency. So what do we perceive the sound to be? Higher or lower pitch than what it actually is. F subscript S is the actual sound source frequency. That is also measured in hertz. And then we have all of these V's here. So as you can imagine, just like any other time we've seen V, it does stand for velocity. But since we have these subscripts, these are all different forms of velocity. So they're not all the same number. 2 out of the 4 are, though. So the V without a subscript is always going to be 343 meters per second. And what this is the speed of sound in air. So it's a constant. So we always have 343 meters per second on top, always 343 meters per second on the bottom. So it is a constant. V subscript D this is the velocity of the detector that'll be in meters per second. Now the detector is who hears the sound. So generally the detector is a person that hears this sound, but sometimes with these problems we could have the detector be an animal. So a dog hears a whistle. Every now and then the detector is an inanimate object, so a sound wave just bouncing off the wall. So the detector is who hears the sound. It can also be, though, like who is detecting the sound. Sometimes it's also referred to as the observer. Now it makes these problems a little ickier than they already look like, is that this number can be positive or negative, and you have to determine if it's going to be positive or negative based on how the detector is moving. So these are problems where if we've kind of gotten to the habit of, like, we're pretty familiar with our symbols and units, we don't really need to read the problem, just skim and scan numbers, plug them in, and we generally get the answer right. We can't do that for these problems. These problems have a lot of detail that we have to pull out from the story to consistently get the correct answer. V subscript S is the velocity of the source. And that is also in meters per second. If you're starting to run out of room, you do have all this white space up here. We could throw this in if you wanted to. But the source is what makes the sound. This can also be positive or negative based on direction. So since they are velocity, which is vector quantities, even though we sometimes can refer to them as speed, or with vector quantities, direction doesn't matter, so you don't worry about it. But these are problems where direction does matter, unfortunately, so gotta worry about direction too. So here's a few of our general rules that we have with direction. So if the detector or the listener or the observer, so whoever it is that listens, hears the sound, moves towards the source, what is giving off the sound, then the velocity of the detector is positive. If they move away, then V subscript D is negative. So if I hear a siren and I move towards the siren, I'm the detector, I move towards the siren, then my velocity will be positive. If I hear the siren and I start to run away, oh no, the cops are chasing after me, then my velocity is going to be negative. And the reverse is also true. So if the source moves towards the detector, Vs is positive. So siren's going, they see a person, drive towards the person. That velocity is going to be positive. If they move away, then Vs will be negative. So any keywords approaching, heading towards, coming close to, all positive directions. Moving away, leaving, exiting, all negative directions. All right, so we're going to do, of course, a couple practice problems here. For these first few problems, really more so today, to make these a little bit easier and to focus a little bit more on the reading and interpreting the problem, we're going to generally have always one thing stationary. So either the source or the detector is stationary, so it's not moving. And then tomorrow we'll do some problems where both stationary, both the observer and the source are moving. All right, so here's what one of these problems might look like. So we have a person sitting on a bench, and a train comes towards the person at a speed of 31 meters per second, blowing a 305 hertz horn. So what frequency horn is heard by the person? So I want to see what frequency does the person hear. So I'm looking for my Doppler frequency. And for our first run through of these problems, we're going to put our equation down here again. And I think walking through each variable of the equation is going to help us to kind of pick out what exactly it is that we're looking for. And to put your mind at ease a little bit here. Oops, I forgot. Why I shouldn't do notes so early in the morning. FS. Doing this before school here. So I got to squeeze in that little FS there. I apologize for that. But we're going to walk through each one of these variables and just kind of pick them out from our story problem here. So we have a person that is sitting on the bench, and a train comes towards the person. I'm going to kind of underline keywords about moving, behavior, and how fast we're going. And they're moving at 31 meters per second, blowing a 305 hertz horn. So the first variable I need is F subscript S. So F subscript S is the frequency of the sound. So what's the actual frequency that the sound source is being emitted? So I need to find my sound source. So what's making the noise? So I have a train moving at a speed, blowing a horn. So the train blowing the horn That's the noise. And so this is the frequency of the horn. So this is the actual frequency that the horn is being emitted at. So my FS is 305 hertz. Next up, I have this V with no subscript. So notice in my problem here, it doesn't mention anything about the speed of sound. So just like all of our other constants, the speed of sound in air, so how fast sound travels through air, is a constant. So you're never going to be given it in the problem. It's just a number in your toolbox always to pull and use whenever you need it. Next up, I have V subscript D. So this is how fast does the detector move? How fast is the detector going? So I first need to figure out these two things in my story, the person or the train, who's the detector and who's the sound source. So I have a person sitting on a bench. Train comes towards the person at a speed of 31 meters per second. What frequency of horn is heard by the person? So the detector is whoever hears the sound. So heard by the person. So the person here is my detector. So they are the one that hears the sound. They're detecting the sound. They are listening to the sound. So I need to think about how fast is my person going. So my person is sitting on a bench. They're not moving. So if they're just sitting down, not moving, their velocity is 0 meters per second. Vs is the source. How fast is the source moving? So that's whatever makes the sound. So a horn makes the sound. So what is the horn attached to? Where's the horn coming from? So I have a train coming by the person at a speed of 31 meters per second blowing the horn. So it's the train blowing the horn. So it's the train's horn making the noise. So how fast is the train going? 31 meters per second. So now since I have value to this velocity, I need to take a second before I just finish writing 31 and decide if I'm going to keep this a positive 31 or if I need to change it and make it a negative 31 based on how the train is moving. So I'm going to use these notes up here to determine that. So anytime the detector or the sound source moves towards the other, it's a positive velocity. And anytime they move away from each other, it's a negative velocity. So for my example problem here, person sits on the bench, train comes towards the person. So towards, that's the same as like approaching, heading to. So towards, this means this is a positive velocity. So I'm going to just leave this number as is, and I'm going to treat it as a positive number. If this said the train was leaving the station, going away from the person, heading away, then I would write this as a negative 31 meters per second. All right, so now I can plug in our numbers. So Fs, I look in my givens here, that's 305 hertz. Parenthesis, 343 meters per second for speed of sound, plus 0 meters per second, over 343 meters per second. Now, remember this sign here is a minus. So I need to write this as a minus. I don't change this as a plus because my velocity is positive. I just use this as a positive velocity. So minus a positive 31 meters per second. And if this velocity was negative, because the train was leaving away, then I write this as a negative 31. And down here, I would then write this as 343 minus a negative 31. So I do suggest you try entering this in your calculator with me. So if we need to, we can pause the video, give people some time to put this in their calculator to try it out, see what they get. If you happen to get a different answer, your neighbor got it right, like check with them, see their work. But we're going to add what's in the parentheses, and we're going to multiply these two values together before dividing over what this value is. And so when we do that, you should get 335 hertz. 335 hertz. Another strategy you could do if you didn't want to enter all this in your calculator is work with it separately. So 305 times 343, get that number over, then just subtract this 312. I think it's little extra steps, but it does eliminate a calculator error for you. So you are more than welcome to do that too if that's easier for you. But we get about 335 hertz for our Doppler frequency. So now what's nice about these problems is I can see if my answer makes sense as a way to check to see if it's right. So in this problem, the train is coming towards the person. So if the train's coming towards the person, those sound waves should be getting compressed. And so that person should be hearing a higher frequency sound than what the sound actually is. So my Doppler frequency, 335, is bigger than 305. So we should be all set and good to go. So down here, we're going to take a minute to try one of these on our own. It's the exact same problem as above, but now the train is going past the person. So now the train is leaving, moving past the person. So now the train has a negative velocity. So I'd still like you to read through and practice picking out our variables, even though I told you, hey, it's pretty much the same problem here. But now we have that Vs is negative. So now we're going to see what is that going to do to our Doppler frequency now that the train is moving away. So we should be getting a frequency that is less than the actual frequency, since those waves are getting stretched out and they're getting a little elongated here. But now we're going to see mathematically if that is going to be true. So we're going to take a second to pause the video, give everyone a couple minutes to work through the problem, see what kind of frequency they get, and then we'll resume the video and see what the work should look like. Okay, so with our work being done here, we're going to check our work, check our answers. So here's my equation. Oops. Oh my goodness. Should be using pencil here. So speed of sound plus the speed of the detector, speed of sound minus the speed of the source. So the person's still on the bench as the train goes by the person at a speed of 31 meters per second, blowing the same horn. What frequency horn does the person hear now? So FD, and is my Doppler frequency. Fs is the frequency of the sound source. So in this case, it's the horn still making the sound. So the horn has a frequency of 305 hertz. Speed of sound in air is a constant, 343 meters per second. So even though that's not in my problem, that's there for me to use. Detector. So who hears the sound? So person on the bench, train goes by the person. What horn is heard by the person? So my person is still the detector, and they are still sitting on the bench. So their velocity is still 0. Sound source, so that's my train. So train goes by the person, they blow a horn, makes this sound. So train's the sound source, and the train is moving at 31 meters per second. So I mentioned before we started this problem that we have their speed here, but they're going past the person. So they're leaving the person, heading away. This is going to be a negative velocity. I'm going to use it as a negative number when I put in my formula here. So 305 hertz over 343 plus 0 over 343 minus a negative 31 meters per second. So I highly suggest you don't start changing these signs, even though, yes, we are going to add this here. 343 minus a negative does give us a positive. I highly suggest you don't start changing these signs, because when we start changing these signs for one problem, we start to edit it here. So like, since we made this a plus here, the next time we do another problem, we might just start off with what I accidentally did here with this is a plus on the bottom because we added it down here, and that's not what we want. Always starts off with a plus on top, minus on the bottom. So I highly encourage you just throw in the negative, plus a negative, minus a negative, and that generally keeps us from ever changing these signs. If we start changing them ourselves, then we kind of forget what we should be starting these signs off as being. Just a helpful hint after doing this for 10 years. So my Doppler frequency, so 343 plus 0 times 305 over 343 minus a negative 31 meters per second. So we should have gotten 279.7 hertz around there, which we can round up here to about 280 hertz. You have though 279.7, that's absolutely fine. But to check our work, so my Doppler frequency here, 280 is less than 305. And if the train is moving past the person, leaving away, then we should be getting a lower frequency that is perceived. So our answer we can use to double check our work. So 280 is less than 305. So we can feel pretty comfortable that we probably answered this question correctly, probably had our numbers where they're supposed to be. All right, so now you're going to work through 5 or 6 of these problems on your own. I have another video posted for the day of me walking through the first problem out loud. So if you're feeling pretty comfortable, you can start on your own. But if you want to see one more example, if our fabulous sub today could administer first those worksheets. And then if you want to see one more example, we'll pull up, we'll do this regardless, but we'll pull up the second video attached to the work for the day. And we'll play that so that way we can get one more practice problem with these crazy Doppler effect equations. And that is it for our notes for the day.